Hi, welcome to my class in graph theory. The study of graphs, or this course graph theory, originated with a problem known as the Konigsberg bridge problem. The Konigsberg bridge problem. Konigsberg was the original capital of Prussia, and Prussia was historically a German state, but it was abolished in 1932, though not legally, when the powers from the Prussian government was transferred to Chancellor Franz von Papen. That was in 1932. But Prussia was legally abolished, that is by law, in 1947. And Konigsberg was the original capital of Prussia. But in 1701, the capital of Prussia was changed to Berlin. Now, there was a river in Konigsberg. In this diagram, the river is indicated by this shaded region, or this shaded part of the diagram. This represents the river. The river goes from here to here. And this river divided the city of Konigsberg into four land masses, or four land areas, or four regions, which I denoted by capital letter with a subscript. The four regions are, this is the first region, this is the second region. This is the third region denoted by R3. And this is the fourth region denoted by R sub 4. Again, there was a river in Konigsberg. And the river divided the city of Konigsberg into four land areas or regions: R1, R2, R3, and R4. But these four regions, or four land masses, are linked together, or they are connected by 7 bridges. And in this diagram, I denoted the 7 bridges by capital letter B with a subscript. This is the first bridge, denoted by B1, that links region 1 and region 2. This is the second bridge, denoted by B2, that connects region 1 and region 2. Hence, there are 2 bridges, B1 and B2, that link regions 1 and 2. The third bridge is denoted by B3, and this bridge links region 1 and region 4. And another bridge denoted by B4 connects region 1 and region 4. Thus, there are also 2 bridges that link regions 1 and 4. The fifth bridge links, this is the fifth bridge denoted by B sub 5, links region 1 and region 3. And the sixth bridge links region 2 and region 3. The sixth bridge is denoted by B sub 6, and the last and seventh bridge, denoted by B sub 7, links regions 3 and 4. The residents of Konigsberg wondered if it were possible to cross each of the 7 bridges, exactly one, and return to where they started. For instance, if a resident lives in region 1, is it possible for this resident living region 1 to cross each of the 7 bridges, exactly one, and be able to return to his place of origin, or region 1? And this problem was solved by Swiss mathematician whose name is The problem of Konigsberg bridge was solved by Leonhard Euler, a Swiss mathematician. And the method he used in solving this Konigsberg bridge problem was considered by many as the beginning of the study of graphs, or the beginning of graph theory. Now, we will convert this Konigsberg bridge problem into a graph by representing the 7 regions as vertices, and we will call these vertices. We will denote these vertices by the notations we use to denote the 4 regions or the 4 land areas: R1, R2, R3, and R4. So this will be R2. The second region, R2, will be denoted by a vertex, and we will call this vertex R sub 2. And the first region, denoted by R1, will be represented in a graph by a vertex, and we will call this vertex R1. The fourth region, we represent this fourth region or this fourth land area will be represented in the graph by another vertex, and we call this R4. And the third land mass or land area will be represented by another vertex. We will call this vertex R sub 3. In the graph, we will represent the 7 regions that connect 2 regions or that link 2 regions by lines. And we call these lines in a graph as the edges. Since there are 2 bridges that link region 1 and region 2, in the graph we connect these vertices R1 and R2 by 2 lines or by 2 edges. A line or an edge from vertex R1 to R2 would represent the first bridge B1 that links R1 and R2. And we call this as E1. Or we might as well call this line as capital B1. And this edge or this line B1 represents the first bridge B1 that links the region 1 and region 2. There is another bridge that links region 1 and region 2, the second bridge B2. Thus, we connect these 2 vertices R1 and R2 by another line, or we call it edge in a graph. And we call this B2. This edge B2 represents the bridge B2, the second bridge B2 that links region 1 and region 2. Now, there are also 2 bridges that link regions 1 and 4. That means in our graph, we have to connect the vertices R1 and R2 by 2 lines. And we will denote these lines or edges by B3 and B4. A line from R1 to vertex R2 would represent the third bridge B3. And this edge B3 represents the third bridge that links region 1 and region 4, denoted by vertex R1 and vertex R2. And another bridge denoted by B4, we represent that by a line that connects R1 and R2. And this second line that connects R1 and R4 is an edge that we will call B4. Now, the fifth bridge links region 1 and region 3. In our graph, we connect vertices R1 and R3, representing the two regions connected by the bridge B5, which we represent by a line that goes from vertex R1 to vertex R3. And we call this line, we denote this line or this edge as B5 for bridge B5 for the fifth bridge. And for the sixth bridge, we draw a line that connects vertex R2 and R3. This is vertex R2 and R3, and we should connect them with a line. This line represents the bridge denoted by B6. So we might as well represent this edge or line by B6. Represent that B6 is the sixth bridge that connects region 2 and region 3. And finally, the last and seventh bridge is the bridge that links regions 3 and 4. In our graph, the seventh bridge will be represented by a line that connects the vertex R3 representing region 3 and the vertex R4 representing region 4. We construct that line. And this is B7. So we have translated the Konigsberg bridge problem into a graph. The problem now is to find a closed walk or a closed path that will start from any vertex in this graph and that traverses each of the 7 edges of this graph exactly once, and the path must end at the same vertex. The closed path is what is known as Eulerian circuit. Eulerian circuit. Eulerian circuit is a closed path that starts with any vertex and that traverses each of the edges of the graph and that returns to the same vertex. That closed path is known as Eulerian circuit. If we can find that Eulerian circuit from this graph, then we have solved the Konigsberg bridge problem. We have found a path that starts from a region and that crosses each of the 7 bridges exactly once and return to that same region where we started. And so for now, you try to solve this Konigsberg bridge problem, but do not try to cheat and look for the solution in the internet. We consider again the graph that represents the Konigsberg bridge problem. But I will add an edge to this graph that connects vertex R3 with itself. Hence, you can see from this diagram that a graph consists of vertices R1, R2, R3, and R4. And a graph consists of edges. In this graph, we have edges B1, B2, B3, B4, B5, B6, and B7. And we can collect the vertices into one set, and we can also collect all the edges into one set, and we now formally define graph. This is the formal definition of a graph. Graph is a pair of sets denoted by capital V and capital E, where capital V is the set of vertices and capital E is the set of edges. Again, a graph is a pair of sets VE, where V is a set of vertices and E is a set of edges. For this graph, our set V is the set of vertices. Hence, this set V will consist of elements R1, R2, R3, and the fourth vertex R4. You remember that in the Konigsberg bridge problem, these vertices represent the four land masses. And our set capital E, the set of edges for this graph, will consist of elements. The edges are B1, B2, B3, B4, B5, B6, B7, and this edge that I added that connects vertex R3 with itself, I will denote this by B8. So this is the set of vertices for this graph, and this is the set of edges for this graph. But the set of edges, capital E, instead of writing capital B1, B2, B3 up to B sub 8, we can be more specific by specifying the vertices that are connected by each edge. Example, this edge capital E can be written as the edge B1 is an edge that connects vertices R1 and R2. Instead of writing B1, we write the pair R1, R2. And the second edge B2 also connects the same vertices R1 and R2. Instead of writing edge B2, we write the pair R1, R2. Now this pair, instead of writing R1, R2, you can write R2, R1, which means that the pair is not ordered, which means that the edge R1, R2 or this edge R1, R2 is the same as the edge R2, R1. This implies that a pair is not ordered. Now for this edge B3 that connects the vertices R1 and R4, we can write, instead of writing B3, we write R1, R4. And for the edge B4, instead of writing B4, we can write R1, R4. Since edge B4 also connects the same vertices R1 and R4. For the fifth vertex, for the fifth edge, instead of writing B5, we write the pair R1, R3. And for B6, we write R2, R3. For the edge B7, we write the pair R4, R3. And for the last edge B8, we write R3, the pair R3. R3, R3. Again, in writing the set of edges in this way, instead of writing R1, R2, you can write R2, R1. The same with R1, R4, instead of writing R1, R4, you can write R4, R1. That means in graph theory, the pair is not ordered. The same with R1, R3, instead of writing R1, R3 for edge B5, you can write R3, R1. For R2, R3, for the edge B6, instead of writing R2, R3, you can write R3, R2. And R4, R3 for the edge B7, instead of writing R4, R3, you can write R3, R4. Now you can see from this set of edges that a pair is repeated. Like the pair R1, R2 is repeated twice. The pair R1, R4 is repeated twice. Hence, we say that the set of edges in a graph is a multi-set. Again, the set of edges in a graph is a multi-set, which means that in the set of edges for the graph, a pair of vertices may be repeated. That means that an edge has a multiplicity. For instance, the edge B1, connects the vertices R1 and R2. So this edge, the edge through vertices R1 and R2 has multiplicity 2 because this pair R1 and R2 appears twice in the set of edges. Similarly, the edge through the vertices R1 and R4 has multiplicity 2. These two, the edge through R1 and R4 has multiplicity 2 because this pair R1 and R4 appears twice in the set of edges for this graph. But R1 and R3 has multiplicity 1 because the edge through R1 and R3 has multiplicity 1 because the pair R1 and R3 appears only one time in the set of edges for this graph. The same with R2, R3, the edge through vertices R2 and R3 has multiplicity 1 because this pair R2, R3 appears only one time in the set of edges for this graph. R4, R3, the edge through R4 and R3 has multiplicity 1 because this pair R4, R3 appears only one time in the set of edges for this graph. And finally, this edge has also multiplicity 1. The edge V8 that connects the vertex R3 with itself has multiplicity 1 because this pair R3 and R3 appears only one time in the set of edges for this graph. Now we have additional terminologies before we continue with the study of graph. The first is end vertices. Consider this edge B1. B1 is an edge that connects the vertices R1 and R2. Or B1 is the edge that links vertices R1 and R2. These vertices R1 and R2 are the end vertices of edge B1. For B2, the end vertices of edge B2 are also the vertices R1 and R2. For the edge B3, the end vertices for the edge B3 are the vertices R1 and R4. Similarly, for edge B4, the end vertices for edge B4 are R1, vertex R1, and vertex R4. For the fifth edge B5, the end vertices are R1 and R3. For the sixth edge, the end vertices are R2 and R3. And for the seventh edge, the end vertices are R4 and R3. And for the last edge B8, the end vertices are vertex R3 and itself R3. Now, when do we say two edges are parallel? Two edges are parallel if they have the same end vertices. Again, parallel edges are edges that have the same end vertices. Examples are the edges B1 and B2 are parallel edges because they have the same end vertices. The end vertices of edge B1 are R1 and R2. The end vertices of edge B2 are R1 and R2. Hence, the edges B1 and B2 are parallel edges because they have the same end vertices. Similarly, the edges B3 and B4 are parallel edges. The end vertices of edge B3 are R1 and R4. The end vertices of edge B4 are R1 and R4. Therefore, edge B3 and edge B4 are parallel edges because they have the same end vertices. Now, a loop is an edge that have the same end vertices. Now, this edge B8 that connects vertex R3 with itself is an example of a loop because the end vertices of the edge B8 are the same, the vertex R3 and R3. So this edge B8 that connects vertex R3 with itself is an example of a loop. An empty graph is a graph where the set of edges is an empty set. That means that the graph consists only of vertices and there are no edges that connect any two vertices in the graph because the set of edges for the empty graph is a null set or an empty set. A null graph is a graph whose set of vertices is a null set or empty set. If the set of vertices in the graph is a null set or empty set, that means that naturally the set of edges is also empty. That means there is actually no graph, and that graph is known as a null graph. Again, an empty graph is a graph whose set of edges is empty or a null set. That means the graph consists only of a set of vertices. A null graph is a graph whose set of vertices is an empty set or null set, which means that there are also no edges in the graph, which implies that there is actually no graph. Now, a trivial graph is a graph that consists of only one vertex. Again, a trivial graph is a graph that consists of only one vertex. Or if you write the set of vertices V for the trivial graph, the set V will consist of only one element. Now the adjacent edges are edges that share a common endpoint. Example, or end vertices. Adjacent edges are edges that share common end vertex. Example, this edge B1 and B2 are adjacent edges because they share two end vertices. They have a common end vertex R1, they have a common end vertex R2. The edge B1 and B6 are also adjacent edges because they share a common end vertex R2. R2 is an end vertex of this edge B1, and R2 is also an end vertex of this edge B6. These edges B1, B2, B6 are adjacent edges. They share a common end vertex R2. Also, these edges B1, B2, B5, B4, and B3 are adjacent edges because they share a common end vertex R1. Now this edge this edge B7 and B5 are also adjacent edges because they share a common end vertex R3. Also, the edges B6, B5, B7 are adjacent edges because they share a common end vertex R3. For better understanding of the terminologies that we have, consider the following graph. This graph consists of vertices V1, V2, V3, V4, and V5. So we say that in symbols, we say that this is the graph G that consists of the set of vertices V and the set of edges E. Or as we defined earlier, graph is a pair of sets, set V, capital V of the set of vertices and set capital E for the set of edges. For this particular graph, the set V is the set of vertices consisting of the vertices V1, V2, V3, vertex B4, and the vertex B5. And the set capital E, or the set of edges, is the set consisting of edge E1, edge E sub 2, the edge E sub 3, the edge E4, the edge E5. Or you can write the set of edges. Instead of writing E1, you can write the pair V2, B1, which is the same as the pair B1, B2. Because as we said earlier, in graph theory, pair is not ordered. And the edge E2 will be the pair B2, B5, or B5, B2. And the edge E3 will be the pair B5, B5. For the end vertices, each of the edges has two end vertices. For the edge E1, the end vertices of edge E1 are the vertices B1 and B2. For the edge E2, the end vertices are B2, B5. For edge E3, the end vertices are B5 and itself, B5. For the edge E4, the end vertices are B4 and B5. For the edge E5, the end vertices are vertices B4 and B5. Now, parallel edges, we defined earlier, are edges that have the same end vertices. In this example of graph, the edges E4 and E5 are parallel edges. The end vertices of edge E4 are vertices B4 and B5. The end vertices of edge E5 are vertices B4 and B5. Hence, edges E4 and E5 have the same end vertices, therefore edges E4 and E5 are parallel edges. A loop we defined earlier is an edge that connects a vertex to itself. In this example, edge E3 is a loop because it connects the vertex B5 with itself. Thus, edge E3 is a loop. We say a graph, simple graph. We say a graph is simple if the graph does not contain parallel edges, and it does not contain loops. And this particular example of a graph is not a simple group because it contains one loop, the edge E3, and one pair of parallel edges, the edges E4 and E5. Thus, this example of graph is not a simple graph. Adjacent or adjacent edges are edges that share a common end vertex. Edge E1 and edge E2 are adjacent edges. They share a common end vertex V2. Edge E2 and the edge E4 are adjacent edges. They share a common end vertex B5. Edges E2, E4, E5, and E3 are adjacent edges. They all share a common end vertex, vertex B5. Adjacent vertices, two vertices are adjacent if there is an edge that connects these two vertices. So these vertices B1 and B2 are adjacent vertices because there is an edge that connects these vertices B1 and B2, edge E1. And vertices B2 and B5 are adjacent vertices because there is an edge that connects vertices B2 and B5. Vertices B4 and B5 are adjacent vertices because there are two edges. These parallel edges connect these two vertices B4 and B5. These vertices B2 and B4 are not adjacent vertices because there is no edge that connects these two vertices B2 and B4. Also, vertices B1 and B5 are not adjacent vertices because there is no edge that connects vertex B1 with vertex B5. The degree of a vertex, say vertex B, or vertex B, the degree of a vertex B denoted by B of B is defined as the number of edges that have vertex B as an end vertex. Again, the degree of a vertex B denoted by B of B is the number of edges that have vertex B as their end vertex. We start with V1. The degree of vertex B1 is the number of edges that have V1 as an end vertex. And the degree of B1 is 1 because there is only one edge, edge E1, that has V1 as an end vertex. We write that. Again, the degree of vertex B1 is 1. The degree of vertex B1 denoted by D of B1 is the number of edges that have B1 as an endpoint, as an end vertex. And there is only one edge with B1 as an end vertex, that is edge E1. Thus, the degree of the vertex B1 is 1. Consider vertex B2. What is the degree of vertex B2? Denoted by B of B2. The degree of vertex B2 is the number of edges with B2 as an end vertex. And there are two edges edge E1 and edge E2 that have B2 as an end vertex. Therefore, the degree of vertex B2 is 2. Now, this vertex B3, what is the degree of vertex B3 denoted by D of B3 is the number of edges that have B3 as an end vertex. And you can see from this graph that there is no edge that has vertex B3 as an end vertex. Therefore, we say the degree of vertex B3 is 0. Now, vertex B4, what is the degree of vertex B4 denoted by D of B4? The degree of vertex B4 is the number of edges that have the vertex B4 as an end vertex. And there are two edges in the graph. Edges E4 and E5 that have the vertex E4, B4 as an end vertex. Therefore, the degree of vertex B4 is 2. And finally, the vertex B5. The degree of vertex B5 is denoted by D of B5. And you can see from this graph that we have a loop at vertex B5. And that is edge E3 that connects the vertex B5 to itself. Or E3, edge E3 is what we call a loop. Now, in finding the degree of a loop, by convention, the degree of a loop is 2. For example, if this is a vertex V and there is a loop at vertex B, then by convention, the degree of vertex B where we have a loop is 2. That is, again, by convention, the degree of a vertex with a loop that is connected by a loop is 2. Now we find the degree of vertex B5 where we have a loop at vertex B5. Then the degree of vertex B5 is the number of edges that have B5 as an end vertex. And we have 1, edge E4. Edge E4 has B5 as an end vertex, so that's 1. Edge E5 has vertex B5 as an end vertex, so that's 2. And for the loop is counted as 2. So the degree of vertex B5 is 2 for the loop, plus 1 for edge E4, plus 1 for edge E5, and that's a total of 4. Therefore, the degree of vertex B5 is 4. Again, when getting the degree of a vertex where you have a loop, the loop by convention is counted as contributing 2 to the degree of the vertex with a loop. Now, pendant vertex. Vertex is called a pendant vertex if the degree of that vertex is 1. And in our graph, there is one vertex B1 with a degree of 1. Therefore, the vertex B1 is a pendant vertex because the degree of vertex B1 denoted by D of B1 is 1. Now, pendant edge is an edge that has a pendant vertex as an end vertex. And edge E1 is an example of a pendant edge because this edge E1 has the vertex B1, which is a pendant vertex, as one of its end vertices. Therefore, edge E1 is a pendant edge because it has vertex B1, which is a pendant vertex. And B1 is a pendant vertex because the degree of vertex B1 is 1. An isolated vertex is a vertex whose degree is 0. And in this example of graph, the vertex B3 is called an isolated vertex because we have shown that the degree of vertex B3 denoted by B of B3 is 0. Now for your practice, consider the following graph. This graph is a representation of this electric network. This electric network has been translated to a graph, and these are the vertices. And for naming the edges of this graph, you have to use pair of vertices. For instance, this edge would be represented by the pair P and Q. And for this graph, you write the end vertices for each edge. For this edge, the end vertices are P and Q. For this edge, the end vertices are Q and R. You also try to find out if there are parallel edges, if there are loops, and try to determine if this graph is a simple graph. Determine what edges are adjacent edges from this graph. Determine the adjacent vertices. You also determine the degree of each of the vertices of this graph. Find out if there is a pendant vertex or if there is a pendant edge. And determine if there is an isolated vertex. An isolated vertex is a vertex whose degree is 0. A pendant edge is an edge that has a pendant vertex as its end vertex. And a pendant vertex is a vertex whose degree is 1. And we define the degree of a vertex as the number of edges that has that vertex as an end vertex. And we define adjacent vertices as vertices that are connected by an edge. We define adjacent edges as edges that have a common end vertex. And we define simple graph as a graph that contains no parallel edges and no loops. And we define a loop as an edge that connects a vertex to itself. And we said that parallel edges are edges that connect the same end vertices. Or parallel edges are edges that have the same end vertices. And if you have any question about the lesson today, you ask your question in the comments below. And we will continue in the next lesson for our course in graph theory. And thank you. Don't forget to subscribe to my YouTube channel, Art Kalisan.